talk about conservation of energy. Conservation just means something does not change. So, the energy that we're looking at does not change. So, the energy at any one time, the total energy at any one time, has got to equal the total energy at any other time. Now, remember the picture I gave you of the bowling ball hitting the pins? Any moving object can do work on another object. So when we look at this, we have to look at the total energy done by the system. The total mechanical energy that we deal with is kinetic energy plus potential energy. Now we're dealing with mechanical energy. We're going to discuss different types of energy later. Now, total energy is conserved when there are no external forces, when you have no friction, when you have no air resistance, when you have no dissipative, D-I-S-S-A-P-A-T-I-V-E, forces. Now, energy is always conserved. So, say we have our bowling ball and our pin, and say there is friction, okay, of some sort. If I include the friction in my system, then I'm accounting for all of the energy, and all of the energy is conserved. So, as if I have some kinetic energy and some potential energy at any given time, then this has to equal the sum of the potential energy plus kinetic energy at any other time. So they're inversely related. As my kinetic energy goes up here, my potential energy has to go down because this is a constant. Now let's look at these two balls here. The energy of this system is conserved. So if I have my red ball, my blue ball here is going to tend to come to roll down, and let's just say this is my zero potential. Alright, so here my potential energy is zero, so my H is zero here. Clearly the red ball has more potential energy than the blue ball. Let's call this H and D. Let's just say the masses are the same. While my blue ball has potential energy, mgh at, oh, that's at B, isn't it? So when it hits down here and all of the energy for the blue ball has converted to kinetic energy, then the kinetic energy due to my blue ball is going to actually equal my original mgh at B. While the kinetic energy that my red ball experiences when it comes down is going to wind up equaling mgh at D. Up here it's all kinetic energy, and down here it's all, oh excuse me, up here it's all potential energy, and down here it's all kinetic energy. So the total energy at this time is equal to the total energy at this time. Now let's look at a pendulum. Pendulums are a lot of fun. When you pull a pendulum out and you stop it, it is all potential energy. So this is equal to mgh, and the height is this height right here. When the pendulum swings down, it's moving. Now if we've chosen this carefully, this is my h equals 0. So this is all mv squared. It's all kinetic energy. So for a pendulum, this is an excellent example of picking your origin somewhere smart, not the center of the earth. If you pick your origin right at this 0 point of the pendulum, then at the top it's all potential energy, and at the bottom it's all kinetic energy, 1/2 mv squared. And so these become very easy problems where you have mgh is m is 1/2 mv squared. Got my half there. Come on, folks. Gotta remind me. let's look at something interesting. What happens when I solve this for v? V then is the square root of 2gh. If you go back to kinematics, you have seen this formula before. It's the speed to drop an object from a height, h. Now, this is just funny. Falling rock band, look at it. We've got rock band people falling. Okay, it's cute. This is copyrighted. Now let's look at a roller coaster. Roller coasters are a lot of fun. Here is Energy Skate Park from Colorado Fat. At the top of any roller coaster, it's all potential energy, while at the bottom, it's all kinetic energy. Now, let's look at this bar graph. You see the total energy of my skater is not changing, while the kinetic and the potential are inversely related. As the kinetic goes up, the potential goes down. Okay, now let's watch what happens when I add friction. Remember, friction is a dissipative force. So it's going to appear that it's losing energy, but look what happens to this thermal energy. We should see it start going, oh, let's change the coefficient of friction so it makes it move again. Okay, do you see? The sum of all of the energies is still the same. Now he still has his potential energy because we have moved his, pulled him off. That's kind of fun. This is really a fun simulation. Okay, yes, I want to reset. It argues with you. You can pick your skater. You can have a bug going. That's always fun. Okay, let's go okay. So here I've got a bug. You can show their path. You can show a pie chart. You can show position versus time. It's kind of fun. Energy versus time. If you notice, the energy versus time is always constant. If you change gravity, oh my gosh, what happens when we stick this bug on Jupiter? Well, he's having himself some issues. We stick him out in outer space. Okay, this is cool. You ready? Watch. He's going to fly off. Okay, I have way too much fun doing this. All right, on a roller coaster. When you're at a hill, choose your hills carefully. On the hill, it's all potential energy, and that's MGH. In the valley, if you've picked the bottom of the valley as your coordinate 0, then it's all kinetic energy, which is 1/2 mv squared. The same thing with a toy dart gun. When you've, oh heaven help us, I'm about to do a drawing. When you've got it pushed in here, it's all potential energy, and remember that's 1/2 kx squared. That has to equal the kinetic energy when you release it, which is 1/2 mv squared. Now watch what happens when I set these two equal. 1/2 kx squared, this is the compression of your spring, is equal to 1/2 mv squared. Okay, look at this. K over m is equal to v over x squared. I just love symmetry. Isn't that pretty? Now there are other forms of energy. Energy can be considered to be potential or kinetic at the molecular level. For example, thermal energy is a measure of kinetic energy. When I heat particles, they move faster. When you stick your lunch in the microwave and it activates the water molecules and it moves those water molecules faster and faster, you get hot food. So, if it's hot in the room and you don't like the temperature of my classroom, moving around is only going to increase the thermal energy. So if you're hot, sit still. Now chemical energy, we say, is potential energy. So this is the energy stored in food and fuels. So that cupcake you're sitting there eating, folks, that's chemical energy. It's also very tasty. Remember, transformed energy does work. So the rock falling and smashing into the ground changes potential energy into kinetic energy. Now this is very important when we're talking about dams and we're talking about clean energy. Dams take the potential energy of water, all right, and turn it into chemical energy, or turn it into kinetic energy, which tends to turns turbines, and the turbines make electricity. Remember, work is always done when energy is transformed from one object to another. Let me repeat that. It's important. Work is done when energy is transformed from one object to another. Now, there are 6 main types of energy. You need to know the difference in these. Mechanical energy, moving objects. Mechanical, moving. Radiant energy is light waves, is anything that travels in waves, like light and sound. Chemical, stored, like in food and fuels. Heat is thermal. That one kind of makes sense. Now, electrical energy is basically energy transformed that has to do with electricity. We're going to do an entire unit on this. Nuclear energy. It's anything from the nucleus of the atom. This includes fission and fusion, the breaking apart or the pushing together of nuclei. Remember, in general, energy is the ability to do work. Now, let's look at this projectile problem. You guys did not like projectiles when we did them, but let's look at doing all of this from an energy standpoint. Say we have some velocity and it's at some height. The total energy to start with is mgh plus 1/2 mv squared. The energy when he lands is mghl, and let me go and put top here, plus 1/2 mv landing squared. Now, if you have chosen your landing position, well, that's going to be 0. So you get the energy formula. Energy at the top is equal to the energy at his landing is mgh at the top plus 1/2 mv at the top squared. And I'm going to go and put this in here. H landing plus 1/2 mv landing squared. This is my conservation of energy formula for shooting a cannon out at an angle, and my poor guy landing down here. Do you see there is no trig, folks? This is a much simpler problem than the one we did with kinematics. Similarly with springs. When I pull a spring down, my gravitational potential energy is negative. Why? Because it's below my equilibrium. My spring potential energy is a maximum. But think about it. I'm pulling the spring down. My kinetic energy is 0. Oh, yeah, kinetic energy is 0. When I release it and it comes back to its happy place, I see that my gravitational potential energy is 0. My spring potential energy is 0, but I have a maximum kinetic energy. When it pops up above, I have a positive gravitational potential energy because H is positive. My spring potential energy is a maximum, but at the point where it stops, my kinetic energy is 0.